close your eyes. Imagine total silence and pitch darkness. You are aboard a train hurtling through an endless night. This train has no windows, and you can't feel the slightest tremor. How would you know if you were moving? And if you are, where are you going? We are in much the same position, aren't we? Passengers aboard planet Earth, which orbits the Sun, which in turn speeds through the Milky Way galaxy. And our entire galaxy, along with hundreds of thousands of others, is rushing through the cosmic void at an unimaginable velocity, over 2 million kilometers per hour. But unlike that windowless train, we do have a way to look outside. And what we see gives rise to one of the most profound mysteries in modern science. There is an unknown, unseen force pulling entire clusters of galaxies in a single direction. What is this? A gravitational behemoth hidden from our telescopes? Or something even stranger lying beyond the borders of our visible universe? In this lecture, we will travel to the edge of the observable cosmos to try and understand where we are all heading and what the final destination is in this grand cosmic pilgrimage. Ready? Then let's begin our deep dive into the mystery of the Great Attractor. To truly grasp the depth of this puzzle, we need to step back about 100 years to a time when our concept of the universe was completely different. In the early 20th century, most astronomers believed the Milky Way was the entire universe, a massive, yet static and unchanging island of stars where we resided. But then a man named Edwin Hubble stepped onto the stage. Working at the Mount Wilson Observatory, he made two revolutionary discoveries. First, he proved that those nebulous patches of light astronomers saw through their telescopes were, in fact, other galaxies, just as vast as our own, scattered across colossal distances. The universe suddenly became unimaginably larger. But his second discovery was even more profound. Analyzing the light from these distant galaxies, Hubble noticed something peculiar. Their light was shifted toward the red end of the spectrum. This phenomenon, known as redshift, is similar to the Doppler effect for sound. When an ambulance siren approaches, the pitch sounds higher. As it moves away, the pitch drops. The same principle applies to light. Redshift meant that these galaxies were moving away from us. And the most striking observation was that the farther away a galaxy was, the faster it seemed to flee. The inescapable conclusion followed: the universe is not static, it is expanding. All galaxies are flying apart from one another, much like spots painted on the surface of an inflating balloon. This principle, known as Hubble's law, became the foundation of modern cosmology. It presented a picture of orderly, predictable expansion. Every galaxy moved away from every other galaxy at a speed determined by distance. It was elegant, simple, and clear. But as is often the case in science, the devil was in the details. As astronomers measured distances and velocities with greater precision, they began noticing small, yet persistent deviations from this perfect expansion. Galaxies weren't just uniformly flying away, they were also moving sideways, as if something was nudging them off their prescribed course. These small, intrinsic movements, known as peculiar velocities, were the first hint that local forces were acting in the universe, forces powerful enough to counteract the general flow of expansion. This was the beginning of the great cosmic detective story that eventually led us to today's topic. So, picture a massive river flowing smoothly and uniformly in a single direction. That river represents the expansion of our universe, governed by Hubble's law. Every single object, every tiny speck, every cosmic particle should be carried along by this general current. But what happens if we notice that in a specific spot, the water begins to churn, twisting into a powerful whirlpool, and the debris in that area, instead of following the general flow, is pulled sharply off course, rushing toward the vortex center? This is exactly the scenario astronomers began observing back in the 70s and 80s. They were measuring the speeds of galaxies and comparing them to the predictions of Hubble's law. The discrepancies were glaring. Our own galaxy, the Milky Way, along with its closest neighbors, including the Andromeda Galaxy, and our entire cluster, known as the Local Group, is moving at approximately 630 kilometers per second relative to the overall cosmic flow. That staggering velocity translates to more than 2 million kilometers per hour. But relative to what? How do you measure your speed if you're stuck on a windowless train? We needed a definitive reference point, something truly stationary, fixed within the expanding universe. Fortunately, we have exactly that reference point, the cosmic microwave background, or CMB. This is the faint afterglow of the Big Bang, which permeates the entire cosmos. It is spectacularly uniform. Its temperature is almost identical in every direction, hovering at just 2.7 degrees above absolute zero. As the oldest light in the universe, it serves as the perfect cosmic coordinate system. When astronomers pointed ultra-sensitive instruments at this radiation, they detected a tiny anomaly. One half of the sky was a minuscule fraction of a degree warmer than the other. This phenomenon was dubbed the CMB dipole anomaly. There was only one possible explanation. We are moving. Just as raindrops hitting a car windshield appear to rush toward you, the CMB photons coming from the direction we are traveling get a slight boost in energy. Their light is blue-shifted and consequently appears slightly hotter. Conversely, photons arriving from the opposite direction are red-shifted and appear cooler. By measuring this precise temperature difference, scientists could calculate our speed and, crucially, our direction with stunning accuracy. That direction pointed toward the constellations of Hydra and Centaurus. The detectives now had all the evidence: the smoking gun, the victim, our motion, and the precise direction the shot was fired from. All that remained was finding the culprit. Something immense, a colossal concentration of mass, had to reside in that direction, exerting a gravitational pull powerful enough to yank not only our own galaxy, but all its neighbors violently off course. The hunt for this gravitational behemoth began instantly. Armed with knowledge of its general direction, astronomers began meticulously mapping the section of the sky in the constellations of Hydra and Centaurus. The problem was that this critical region of the sky is partially obscured by the plane of our own galaxy, the Milky Way. Dense clouds of dust and gas, along with billions of foreground stars, create the so-called zone of avoidance, or zone of obscuration, making it extremely difficult to see anything clearly through it. It was like trying to find a specific person in a crowd while looking through frosted glass. But gradually, utilizing radio telescopes capable of penetrating the dust and analyzing the motion of visible galaxies at the zone's edge, scientists started to realize that something truly massive was hiding there. In 1986, a group of astronomers, later nicknamed the Seven Samurai, published the results of their exhaustive research. They confirmed that hundreds of galaxies within a radius of hundreds of millions of light-years were exhibiting a synchronized motion, all heading in the same direction. They calculated that creating such an effect required a concentration of mass equivalent to tens of thousands of galaxies like the Milky Way. This hypothetical object, this cosmic center of gravity, was given an intriguing and slightly ominous name, the Great Attractor. Attractor, of course, means something that pulls, and pull it certainly did. Our local group of galaxies, the massive Virgo Supercluster that we belong to, and countless other clusters were all tumbling toward it, like water rushing into a gigantic gravitational whirlpool. But what exactly was it? Was it a single, supergiant object, or an incredibly dense cluster of galaxies? Due to the Milky Way's dusty veil, getting a precise answer was impossible. This sparked decades of debate and intense research. Scientists attempted to estimate its mass by studying the velocity deviations of increasingly distant objects. Each new piece of data added depth to the portrait of this unseen giant. It became clear that this was not merely one cluster, but rather the nexus point where several major cosmic structures, the filaments, or threads of the cosmic web, intersected. The Great Attractor was not a single dot, but an entire region, the gravitational heart of our corner of the universe. But as our instruments grew more sophisticated, allowing us to peer better behind the curtain of the Milky Way, a new, even more intriguing picture began to emerge. The Great Attractor, massive as it was, could not account for the entire magnitude of our velocity. It was responsible for a substantial portion of it, but not all. Something else, something larger and more distant, was also engaged in this cosmic tug-of-war. Imagine you're pulling a rope, trying to budge a heavy box. You strain, you push, and the box starts to move slowly. Now imagine someone invisible steps up behind you and starts helping, adding their force to yours. The box will accelerate. That's essentially how things stood with the Great Attractor. Its pull was strong, but not strong enough. Astronomers realized that beyond it, farther along the same vector of motion, something even more massive must be hidden, something whose gravitational call reached us right through the Great Attractor itself. And they found that something. Roughly 650 million light-years away from us, several times farther than the Great Attractor, lies an unbelievable gravitational behemoth, the Shapley Supercluster. Named after American astronomer Harlow Shapley, it is the largest gravitationally bound structure in the local universe. To put that into perspective, the Shapley Supercluster contains over 8,000 galaxies and boasts a mass 10 million times greater than that of the Milky Way. It is a genuine galactic metropolis, dense, hot, and colossally massive. Unlike the Great Attractor, Shapley isn't obscured by the dust of our galaxy, so we can observe it in all its splendor. It's a seething cauldron where galaxies constantly collide and merge, and the intergalactic space is filled with superheated gas that glows brightly in the X-ray spectrum. Once astronomers factored in the gravitational influence of the Shapley Supercluster, a significant portion of the remaining mystery regarding our velocity was resolved. The picture became clearer. Our galaxy and its neighbors are first pulled toward the closer, less massive Great Attractor, which in turn, along with us and everything else, is falling toward the far more distant and powerful giant, the Shapley Supercluster. Our movement isn't just a flight towards a single point. It's a complex, multi-stage plunge down a gravitational cascade. However, even this seemingly elegant model wasn't complete. Even accounting for the combined influence of the Great Attractor and Shapley, a small but statistically significant component of our motion remained unexplained. It was as if a third, even more powerful and distant helper stood behind the second, stronger one. Everywhere scientists looked, it seemed something even larger was lurking just beyond the horizon. This led to an even bolder and more controversial hypothesis that took the mystery to an entirely new level. What if this wasn't just local attraction, but something far more fundamental? What if our entire region of the universe, spanning 1 billion light-years, is moving as a single unit in one direction, swept along by an unseen flow? This hypothesis was dubbed the dark flow. The term itself sounds like something straight out of science fiction, and fittingly, it describes a phenomenon that barely fits within the parameters of the standard cosmological model. The core idea is that the motion we observe isn't merely gravity pulling us toward local superclusters such as Shapley. Instead, it suggests we are part of a far more massive, coherent bulk flow, dragging hundreds of galaxy clusters along with it. This isn't just a whirlpool in a river, it's the river itself, somehow flowing in a direction it shouldn't be. The authors of this hypothesis, astrophysicists Alexander Kashlinsky, Fernando Atrio Barandella, Daniel Kuchevsky, and Harold Eberling, presented their findings in 2008. Their work was based on analyzing data from the WMAP satellite, which mapped the cosmic microwave background radiation. They utilized a complex method centered on the Sunyaev-Zeldovich effect. Briefly, when cosmic microwave background photons pass through a cluster of galaxies filled with hot gas, they interact with the gas's electrons, receiving a small energy boost. If the cluster is stationary, this effect is direction independent. However, if the cluster is moving, the effect will be slightly amplified in the direction of motion and weakened in the opposite direction. By analyzing this effect across hundreds of distant galaxy clusters, Kashlinsky's team reached a truly shocking conclusion. All these clusters, scattered across a vast region of the sky, exhibited a collective movement in the exact same direction, roughly toward the same region as our own local group. The speed of this flow was estimated to be between 600 and 1,000 kilometers per second. This was staggering. It appeared that a massive chunk of our observable universe, stretching billions of light-years, was behaving contrary to theoretical predictions. According to the Standard Model, gravity-induced movements should average out and dissipate at such enormous scales. The universe on the macro scale should be isotropic and homogeneous. There should be no preferred direction or bulk flows. Yet the dark flow pointed directly to the existence of such a preferred direction. What could possibly be the cause? The authors hypothesized that the culprit might be something lying beyond the boundaries of the observable universe. Perhaps it is a colossal concentration of mass remaining from the pre-inflationary epoch, that is, from before our universe began its rapid expansion. Or, even more exotically, it could be the gravitational influence of other universes within the framework of multiverse theory. The idea of the dark flow ignited a firestorm of controversy within the scientific community. Many researchers treated it with skepticism, pointing to potential systematic errors in the measurements and the inherent complexity of the data analysis. It was simply too radical an idea to accept without irrefutable proof. The criticism leveled against the dark flow hypothesis was entirely warranted. After all, science operates on the principle that extraordinary claims demand extraordinary evidence. The primary objection was that the detected signal was incredibly faint, barely above the threshold of statistical significance. Measuring the kinematic Sunyaev-Zeldovich effect is an extraordinarily delicate and complex undertaking. Furthermore, countless other astrophysical phenomena, or simple noise, could either mimic the signal or introduce significant interference. Critics suggested that Kashlinski's team might not have fully accounted for all these confounding factors, potentially mistaking random fluctuations for a genuine physical effect. All hopes were then pinned on new, more precise data, and that data arrived sooner rather than later. The WMAP satellite was superseded by the European Space Agency's Planck Space Observatory. Planck boasted significantly greater sensitivity and resolution. Its primary objective was to create the most detailed map of the cosmic microwave background radiation ever recorded. Crucially, one of the mission's specific goals was to scrutinize the controversial anomalies detected by its predecessor, the dark flow included. In 2013, the Planck team published their findings. The verdict was disappointing for dark flow proponents. After analyzing data from an even larger sample of galaxy clusters, Planck scientists found no statistically significant evidence for the existence of a coherent flow on those vast scales. They concluded that the signal observed earlier was most likely the result of instrumental errors and insufficient statistical data. The scientific community, by and large, breathed a collective sigh of relief. The standard cosmological model appeared to have held firm. The notion that something beyond the visible universe was influencing us was shelved, a compelling yet ultimately unverified hypothesis. The research focus subsequently shifted away from exotic external influences and returned to the more grounded, though no less complex, study of large-scale structure within our own, observable universe. However, Kashlinski and his supporters refused to concede. They argued that the analysis methods used by the Planck team were not entirely appropriate for detecting this specific type of signal. They also suggested that certain masks used to remove foreground contamination from our own galaxy might have inadvertently erased the faint dark flow signal itself. The debate continues to this day, albeit with far less intensity. While the majority of cosmologists consider the matter closed, a few holdouts still believe that the data might conceal hints of this grand anomaly. This entire episode serves as an excellent illustration of the scientific method in action. A hypothesis is proposed, subjected to increasingly precise experiments, and is ultimately either confirmed or disproven. Even if the dark flow turned out to be a mirage, the rigorous search for it forced scientists to deepen their understanding of the universe's structure and develop innovative new analytical techniques. While the dark flow debate raged on, another team of researchers, led by Brent Tully at the University of Hawaii, took a fundamentally different approach. Instead of searching for distant hypothetical causes of our movement, they decided to first create the most accurate map possible of our local cosmic neighborhood. Their focus wasn't the cause of the motion, but the kinematics, specifically how galaxies move relative to one another. For years, They meticulously gathered velocity data for thousands of galaxies in our region. They constructed a 3D map where each galaxy was represented not just as a dot, but as a vector indicating the direction and speed of its peculiar motion. Its inherent movements separate from the universal expansion. Once sufficient data was compiled, they took the next crucial step, mapping the gravitational field of the region. The underlying idea is straightforward. If a galaxy deviates from the general flow of cosmic expansion, it is being pulled by gravity. By analyzing these deviations, they could reconstruct the distribution of mass, including the dark matter responsible for the pull. The culmination of this monumental effort was a publication in 2014 that fundamentally changed our understanding of our place in the cosmos. Tully's team revealed that our Milky Way galaxy is part of a colossal, previously unrecognized structure they dubbed Laniakea. Translated from Hawaiian, the name means immeasurable heavens, and it couldn't be more fitting. Laniakea is a supercluster of galaxies, but it's defined not merely by the concentration of light, but by its overall gravitational influence. It functions as a massive gravitational basin. All galaxies within Laniakea, and there are roughly 100,000 of them, are flowing toward a shared center of mass, much like water pooling into a vast, unseen ocean. The Great Attractor, which we previously considered a distinct object, turned out to be merely the deepest point of this basin, the floor of a gravitational valley that we are all slowly draining into. Laniakea spans approximately 520 million light-years across and contains the mass of 100,000 trillion suns. This new concept provided a fresh perspective on our cosmic motion. We aren't simply hurtling towards the Great Attractor, we are part of an immense gravitationally bound system, and our movement is the natural outcome of residing within it. The Virgo Supercluster, once thought to be our cosmic home, is revealed as just a small suburb in this galactic megalopolis. Beyond Laniakea lie other similar structures, such as the Perseus-Pisces supercluster, separated from us by vast cosmic voids. The boundaries of Laniakea are defined precisely where the gravitational pull equalizes, causing galaxies to begin flowing away, drawn instead toward a different gravitational center. The discovery of Laniakea was a massive leap forward. It gave us a new cosmic address: Earth, Solar System, Milky Way, Local Group, Virgo Supercluster, Laniakea. This helped explain much of our movement as a result of residing within this gigantic gravitational basin. But even this elegant model wasn't perfect. One small, nagging problem remained. When researchers modeled the movement of galaxies inside Laniakea, they found that the theoretical speed at which we should be moving toward the Great Attractor was still slightly slower than the observed speed calculated from the cosmic background radiation. They were short one key component. So scientists asked, what if we're not only being pulled forward, but also being pushed from behind? Gravity, as we know it, is a force of attraction. But on cosmological scales, the effect can appear different. Imagine a vast region of space where matter density is significantly lower than average. This region is called a void, or a cosmic emptiness. This area, depleted of galaxies and dark matter, will exert less gravity than its denser surroundings. If our galaxy sits on the edge of such a void, the denser areas will pull us harder than the empty region. Effectively, it looks as if the void is pushing us away. This is not some new anti-gravitational force. It's simply the result of uneven gravitational distribution. Studying the galaxy distribution map in the direction opposite to our motion, the same team of astronomers who discovered Laniakea found exactly such a structure. It was a massive, previously unknown area of emptiness, almost completely devoid of galaxies. They named it the dipole repeller. It turns out this repeller contributes significantly to our movement. It creates the effect of a gravitational hill behind us, from which we essentially roll down toward the gravitational valley of the Great Attractor. Thus, our movement is the result of a complex dance of two forces: the carrot ahead, the Great Attractor, and the stick behind, the dipole repeller. These two factors, attraction and apparent repulsion, together almost perfectly, explain the observed speed and direction of our local group of galaxies. The puzzle that had plagued astronomers for half a century finally received a coherent and elegant solution. It required no exotic hypotheses about influence from outside the known universe. The answer had been here all along, hidden within the complex and invisible architecture of the cosmic web. Now let's put all the pieces of this cosmic puzzle together and look at the big picture we've assembled. Modern cosmology doesn't describe the universe as a uniform soup of galaxies, but rather as a gigantic three-dimensional structure resembling a massive web or a sponge. This structure is famously known as the cosmic web. The cosmic web is built from dense strands or filaments, at whose intersections massive clusters and superclusters of galaxies are formed. Stretching out between these filaments are enormous, almost entirely empty regions known as voids. Galaxies aren't scattered randomly, they are born and reside along these filaments, slowly draining towards the gravitational nodes, much like dewdrops sliding down the threads of a spiderweb. We can now precisely chart our journey within this cosmic structure. Our galaxy, the Milky Way, along with the local group, is part of the Virgo Supercluster. In turn, the Virgo Supercluster is just one of the many arms of the gigantic Laniakea Supercluster. Laniakea itself functions as a massive gravitational basin. At its heart lies the Great Attractor, a dense concentration of galaxies centered on the Norma cluster. Consequently, our primary motion is directed straight towards this center. We are, essentially, falling toward the Great Attractor. But that is only half the story. Directly opposite to us is the dipole repeller, a massive void, an area characterized by very low matter density. Its lack of gravitational pull creates a profound repulsive effect, providing us with an additional push in the exact same direction that the Great Attractor is pulling us. The combined action of these two factors, attraction from the front and repulsion from the rear, determines our total final speed of 630 kilometers per second relative to the cosmic microwave background. Yet the story continues. Laniakea itself, this colossal continent of galaxies, is not stationary. It is moving as a whole toward the even more massive Shapley Supercluster. This means our motion is multi-layered. We are moving within Laniakea, and Laniakea itself is moving through space. It's like a person walking across the deck of a ship, which is sailing down a river, while the river itself flows into the ocean. Each level of motion is nested within another, more colossal one. So what initially seemed like a simple question, where are we headed, turned out to be a complex problem with a deeply layered answer. We aren't simply flying toward a single point, we are participants in a grand cosmic dance, governed by the invisible choreography of gravity and the distribution of dark matter. Studying this dance has allowed us not only to understand our own movement, but also to create an unprecedentedly detailed map of our cosmic neighborhood. What is the true significance of these discoveries? Initially, they might seem highly abstract, completely detached from our everyday lives. Our galaxy is moving at 2 million kilometers per hour. So what? We don't feel it in the slightest. Yet both scientifically and philosophically these findings are immensely important. Firstly, they represent a true triumph of the scientific method. This is a classic detective story. Scientists working with minuscule clues, slight deviations in galaxy motion, and anomalies in the cosmic microwave background were able to unravel this intricate puzzle. They reconstructed a picture of colossal cosmic structures, most of which remain invisible to us because they are predominantly composed of dark matter. It is a powerful demonstration of the human intellect, capable of understanding the laws of the universe while standing on a tiny speck of dust in the vast ocean of space. Secondly, these discoveries fundamentally alter our perception of our place in the universe. The Copernican principle, which states that we hold no special or central position, now resonates with even deeper meaning. We don't just live on an average planet orbiting an average star in an average galaxy. We now know that we are part of an ordinary flow within the massive Laniakea Supercluster, which itself is just one of countless similar structures in the vast cosmic web. This feeling is both humbling, it tempers our pride, and exhilarating, making us feel connected to something unimaginably vast and intricate. Thirdly, studying the large-scale structure and peculiar velocities of galaxies is crucial for testing and refining our cosmological models. By comparing the observed structure to what computer simulations predict, we gain a better understanding of dark matter and dark energy, the two most mysterious components of our universe, which together account for 95% of its total mass energy. Deviations from these predictions can point towards new physics, suggesting that our current theories are incomplete. For instance, had the dark flow hypothesis been confirmed, it would have caused a revolution in cosmology and perhaps provided the first observational evidence of other universes. Although that hasn't happened, the very fact that we can rigorously test such bold ideas speaks volumes about the maturity of our science. This knowledge won't help us solve immediate earthly problems, but it expands our horizons and answers one of humanity's oldest questions. Who are we and where are we? The answer, as it turns out, is far more complex and interesting than we ever could have imagined. What secrets still lie waiting to be unlocked? Despite our immense progress in mapping cosmic motion and structure, the story of the universe is far from complete. Science is a continuous process, and answering one puzzle usually raises several new questions. One of the biggest unanswered questions is, what exactly caused the formation of a structure as intricate as the cosmic web? The prevailing theory suggests that its seeds were microscopic quantum fluctuations that occurred in the first fleeting moments after the Big Bang. These tiny variations in density were subsequently stretched to astronomical scales by cosmic inflation, and over time, gravity molded them into the vast filaments and voids we observe across the universe today. However, this remains a theory, and we require more precise observations to confirm its specific details. New telescopes, such as the Euclid Space Telescope and the Vera C. Rubin Observatory, are designed to create even more detailed three-dimensional maps of the universe. This will allow us to test the predictions of inflation theory with unprecedented accuracy. Another crucial question revolves around the ultimate fate of these grand structures. We currently observe matter converging into denser and denser clusters. Will this process continue indefinitely? Eventually, all the galaxies within our own Laniakea Supercluster are projected to fall toward the Great Attractor and merge into one colossal elliptical galaxy. But what happens to Laniakea itself? Will it continue its long fall toward the Shapley Supercluster? This is where dark energy enters the equation, the mysterious force driving the universe's accelerating expansion. This expansion directly counteracts gravitational collapse. It is entirely possible that this accelerating expansion will eventually sever the gravitational link between Laniakea and Shapley, causing them to move away from each other despite their mutual attraction. Our local group of galaxies will remain gravitationally bound, but everything beyond its boundaries will eventually retreat beyond the cosmological horizon. We will be marooned on a solitary island in an empty, dark universe. By studying the motion of galaxies on these massive scales, we can gain a better understanding of the nature of dark energy and potentially predict the ultimate fate of our cosmos. Furthermore, there are more local, yet equally intriguing, puzzles. We still don't completely understand the precise structure of the Great Attractor, as it remains partially obscured from our view by the dust and stars of the Milky Way. Future observations utilizing radio and infrared wavelengths will be critical in peering behind this cosmic veil and creating a detailed map of this crucial gravitational region. To peer into the future and understand how our knowledge in this field is about to expand, let's take a look at the tools astronomers will soon have at their disposal. Progress in astronomy has always been intrinsically linked to technological development and the creation of increasingly powerful telescopes. And right now, we stand on the cusp of a new era in studying the large-scale structure of the universe. First, there is the Vera C. Rubin Observatory, currently under construction in Chile. This telescope will possess an enormous field of view, enabling it to scan the entire observable sky every few nights. Over 10 years of operation, it will create the deepest and most detailed survey of the southern sky, measuring the positions and properties of billions of galaxies. This will yield a three-dimensional map of the universe with unprecedented scale and precision. We will be able to resolve the structure of the cosmic web in minute detail, discover thousands of new superclusters and voids, and measure their influence on galaxy movements with incredible accuracy. Second, we have the Euclid Space Telescope, successfully launched in 2023. Its primary mission is to study the geometry of the dark universe. Euclid will measure the redshifts of tens of millions of galaxies. This will allow us not only to map their spatial distribution, but also to study how this structure has changed over cosmic time. This will give us the key to understanding the cosmic tug-of-war between the gravity of dark matter, which seeks to pull everything together, and the repulsive force of dark energy. Euclid will measure galaxy velocities with such precision that we can test our current models of the Laniakea Supercluster and the dipole repeller, potentially uncovering even more subtle and large-scale flows. Furthermore, we will be aided by next-generation radio telescopes such as the Square Kilometre Array, or SKA, which is set to become the world's largest radio telescope. The SKA will map the distribution of neutral hydrogen, the fundamental building block for stars and galaxies, across vast volumes of the universe and at various stages of its evolution. Crucially, this will give us a completely new perspective on the cosmic web, independent of the distribution of visible light from galaxies. When combined, all this new data will allow us to transition from having a static map of our cosmic neighborhood to possessing a truly dynamic picture, a full-length feature film about the life and evolution of the universe. We will not only be able to say where we are heading now, but we will trace our entire trajectory billions of years into the past, and even project our journey billions of years into the future. The mystery of the Great Attractor may be close to resolution, but in solving it, we have opened the door to an entirely new field of research that will occupy the minds of astronomers for many decades to come. Let's circle back to the idea of the dark flow. While most scientists consider the Planck data to have definitively refuted it, it's worth recalling that scientific history is full of rejected ideas that later returned in a new light. Is it possible there's still a grain of truth in this hypothesis, perhaps in a modified form? Some researchers continue to analyze the data, actively searching for traces of large-scale anomalies. For instance, there are other oddities in the cosmic microwave background, the CMB, that still lack a widely accepted explanation. One of the most famous is the so-called axis of evil. This is the observation that certain large-scale features of the CMB map, including the dipole anomaly, are surprisingly aligned with the plane of the ecliptic, the plane in which the Earth orbits the Sun. From a cosmological perspective, this alignment is an extremely improbable coincidence. Our solar system is a minuscule speck of dust on the cosmic scale, and its orientation should not correlate at all with the fundamental properties of the cosmos. Most scientists dismiss this as a statistical fluke, the idea being that if you look for anomalies long enough, you're bound to find something, but others suggest it might hint that we're missing something fundamental about the universe, or that the data contains unaddressed systematic errors related to our local environment. Another major puzzle is the cold spot, an anomalously large and cold region on the CMB map. The standard model suggests that fluctuations this vast are highly improbable. One hypothesis explains it by the existence of a gigantic supervoid situated between us and that patch of sky, essentially sucking energy from photons passing through it. But even if that explanation holds up, the sheer existence of such an enormous void challenges certain models of structure formation. What if the dark flow doesn't exist exactly as originally proposed, but instead there are other, more subtle and complex large-scale movements that we simply haven't been able to detect yet? Perhaps it's not a unified flow, but a complex system of currents and eddies within the cosmic web, spanning billions of light-years. Our current models rely on the assumption that the universe is homogeneous and isotropic, meaning uniform in all directions, on large scales. But what if that's only an approximation? What if the real universe is a bit more clumpy and non-uniform than we currently believe? Future surveys, such as the Euclid mission and the Vera Rubin Observatory, will test this fundamental principle with unprecedented precision. If they detect deviations from homogeneity on the largest scales, It could require a complete overhaul of our cosmological paradigm, potentially reviving ideas about the influence of structures lying beyond our cosmological horizon. Let's take a moment to reflect on the philosophical implications of this narrative. The quest to find our place in the universe isn't merely a scientific challenge. It is a profoundly human endeavor. Since ancient times, people have looked up at the stars, trying to understand how the world works and what our role within it is. Every scientific revolution, from Copernicus to Hubble, has consistently moved us further away from the presumed center of creation. First, we believed the Earth was the pivot point, then the Sun, then our galaxy. Today we know we are just a tiny component of the colossal Laniakea Supercluster, a structure that, on a cosmic scale, is entirely unremarkable. This realization can feel sobering. It underscores our insignificance. Yet there is an alternative viewpoint. Instead of feeling insignificant, this awareness that we are part of such a grand and complex system can inspire a profound sense of belonging and genuine awe. We are not detached observers of the cosmos. We are an integral part of it, a product of its ongoing evolution. Our motion through space isn't random wandering. It's a meaningful, predictable journey along the gravitational currents of the cosmic web. We are passengers aboard Starship Earth, following a clearly defined route charted by the invisible forces of gravity. The story of the Great Attractor also teaches us humility in our scientific pursuit. What seemed like a definitive answer in the 1980s turned out to be just one layer of a far more complex picture. What seems like the final answer today, the model of Laniakea and the dipole repeller, may, in the future, be seen as merely a refinement on the path to an even deeper understanding. There is always the possibility that a new discovery awaits us around the next corner, forcing us to re-evaluate everything we thought we knew. Perhaps future generations will view our current cosmic maps the way we view medieval world charts, full of blank spaces and mythical monsters. They will discover structures and phenomena that we cannot even begin to imagine today. And that is magnificent, because this very yearning to look past the horizon is the engine that drives both science and human progress. Our journey toward the Great Attractor is a metaphor for all scientific knowledge. We move from the known toward the unknown, pulled forward by the mysteries the universe presents to us. And while we may never reach the final center or find all the ultimate answers, the journey itself enriches us, making our world and our existence within it more meaningful. To better grasp how scientists actually make these groundbreaking discoveries, let's take a look behind the scenes, into their lab, so to speak. How, in practice, do you measure the speed of a galaxy located hundreds of millions of light-years away? It's certainly not as simple as using a radar gun on a car. The primary tool here is spectroscopy. Astronomers gather light from a distant galaxy and split it into its component colors, a spectrum. Much like a prism splits sunlight into a rainbow. Within that spectrum, we see dark absorption lines created by various chemical elements in the atmospheres of the galaxy's stars. Each line corresponds to a specific wavelength. If the galaxy is moving away from us, due to the expansion of the universe, all those spectral lines are shifted towards the red end of the spectrum. This phenomenon is known as redshift, first measured by Edwin Hubble himself. By quantifying the magnitude of this shift, we can determine the galaxy's recession velocity and, using Hubble's law, estimate its distance. But this speed only accounts for the general cosmic expansion. How do we measure that crucial deviation, that peculiar velocity, the movement independent of the flow? To do that, we need to know the galaxy's distance using a completely independent method, bypassing the need for Hubble's law. This is arguably one of the most challenging problems in modern astronomy. Fortunately, we have several indirect methods, often relying on what we call standard candles. For instance, a specific class of exploding stars, type Ia supernovae, always reach a nearly uniform peak luminosity. By measuring the apparent brightness of one of these supernovae, we can calculate the precise distance to the host galaxy where it exploded. Another key technique relies on the Tully-Fisher relation, which connects a spiral galaxy's rotational velocity directly to its intrinsic brightness. By measuring that rotation speed via the broadening of its spectral lines, astronomers can estimate the galaxy's true luminosity and subsequently its distance. Once we have those two critical values, the observed velocity derived from redshift and the expected velocity calculated based on the Hubble law and the independently measured distance, we can calculate the difference. That difference is the peculiar velocity. This is painstaking, meticulous work, requiring thousands of observations taken with the world's largest telescopes. Every single measurement is prone to error, and only by averaging the data across a massive sample of galaxies can researchers begin to detect overarching trends and large-scale cosmic flows, like the infall toward the Great Attractor. This is precisely why it took decades of dedicated work by hundreds of astronomers worldwide to finally solve this mystery. It wasn't the sudden insight of a single genius, but rather the hard-won result of collective, methodical, and persistent scientific endeavor. Let's explore one fascinating yet often overlooked aspect of this story. What exactly lies at the very heart of the Great Attractor? What constitutes this bottom of the gravitational valley toward which we are all headed? As we've mentioned, it's not a single mysterious object, but rather a region of exceptionally high galactic density. The key structure within this region is the Norma cluster, also known as Abell 3627. This is an incredibly rich and massive cluster of galaxies, situated about 220 million light-years away from us. It contains hundreds of galaxies submerged in a massive cloud of hot gas that glows brightly in the X-ray spectrum. Its mass is estimated to be 1,000 trillion solar masses. However, as we now understand, the Norma cluster is just the densest part of the Great Attractor, not its entire mass. Surrounding it are other, smaller clusters and galaxy groups that collectively generate the total gravitational field. What will happen when our local group, including the Milky Way and Andromeda, finally reaches this area? This event is far off, billions of years in the future, but we can model the process. First, our local group, which is already in the process of merging, the Milky Way and Andromeda will collide in about 4.5 billion years, forming a single, giant elliptical galaxy known as Milkomeda, will enter the outer reaches of the Norma cluster. The cluster's immense gravitational forces will begin to tear our group apart. Smaller satellite galaxies will be stripped away and absorbed by the cluster's larger members. Eventually, the core of our former group, the gigantic Milkomeda, will spiral around the cluster's center several times, losing momentum due to gravitational drag with other galaxies and intergalactic gas. It will ultimately merge with the central, most massive galaxy of the Norma cluster. This process, known as galactic cannibalism, is the primary mechanism by which galaxies grow in dense environments. Thus, our distant future is to become part of an even larger galactic metropolis. This is the inevitable fate for most galaxies lucky enough to have been born near the gravitational centers of the cosmic web. For those situated in the voids, their destiny will be different. They face eternal solitude in the expanding emptiness. So, our journey toward the Great Attractor is not merely a flight, it's a one-way trip heading toward our future home and, simultaneously, toward our gravitational grave. When considering these colossal formations like the Laniakea Supercluster, it's vital to understand that they are not objects in the usual sense of the word. Laniakea doesn't have the sharp boundaries that define a planet or a star. Its boundary, as we've noted, is dynamically defined. It exists at the point where the velocity vectors of the surrounding galaxies shift and change their direction. Crucially, these structures are not gravitationally bound in the long term. This means they are not permanent. The accelerated expansion of the universe, driven by dark energy, works actively against gravity. Gravity is powerful on small scales. It binds together planets, stars, and galaxies. Our own local group, for instance, will remain gravitationally bound forever. But on the scale of superclusters like Laniakea, gravity is simply not strong enough to overcome the repulsive effect of dark energy. In the distant future, billions of years from now, this accelerating expansion will inevitably tear Laniakea apart. Galaxies located on its outer edges will begin to recede from the center faster than they can fall toward it. Ultimately, only the central, most dense region, the Great Attractor, and its immediate neighbors will remain gravitationally bound. Everything else will be swept away by cosmic expansion beyond the event horizon, vanishing from our view forever. This is a rather melancholy outlook. The vast structures we are discovering and mapping today are temporary constructs, relics of a time when matter, not dark energy, was the dominant force in the universe. We are living in a unique cosmological era when we can still observe this grand cosmic web in its full glory. Future civilizations, should they arise hundreds of billions of years from now, will see a vastly different picture. They will see only their own gigantic home galaxy, formed from the merger of the entire local group, surrounded by absolute emptiness. All other galaxies will have fled so far away that their light can never reach them. Such observers might never discover the Big Bang, the expansion of the universe, or the existence of other galaxies. They could easily come to the mistaken conclusion that their galaxy is the entire universe, a tragic return to the limited worldview our ancestors held just a century ago. So when we study the Great Attractor and Laniakea, we aren't merely satisfying our curiosity. We are perhaps collecting the last crucial pieces of information about our universe before dark energy wipes them away forever. This fact lends a special value and indeed a certain urgency to our research. Let's start by returning to the very beginning of our cosmic story, the cosmic microwave background, or CMB. This ancient light not only provides the ideal reference frame for measuring our motion, but it also contains crucial information about the earliest moments of the universe's existence. The minute temperature fluctuations visible on the CMB map are the direct imprints of those original quantum fluctuations that served as the seeds for future galaxies and superclusters. By analyzing the statistical properties of these patches, their size, distribution, and amplitude, cosmologists can determine the key parameters of our universe with incredible precision: its age, composition, and geometry. The model that best describes this data is called Lambda CDM, LCDM. Lambda represents the cosmological constant associated with dark energy, and CDM stands for cold, dark matter. This model posits that the universe consists of roughly 5% ordinary baryonic matter, the stuff that makes up us and the stars, 27% dark matter, and 68% dark energy. This model brilliantly describes the CMB data, but how does it connect to the motion of galaxies? The key is this: knowing the initial conditions, the fluctuation map in the early universe, and the universe's composition, we can run a computer simulation. This allows us to track how gravity causes these initial fluctuations to form the large-scale structure we see today. Modern simulations, such as Millennium or Illustris, track the evolution of billions of particles within massive cubes of virtual space over 13.8 billion years. And what these simulations reveal aligns strikingly well with the observed cosmic web. In these models, we witness the formation of filaments, voids, and massive clusters at the nodes of the network. We can even measure the velocities of these virtual galaxies and compare them directly to real-world observations. It turns out that flows, such as the infall toward the Great Attractor, are a natural and inevitable consequence of structural evolution within the Lambda CDM model. Thus, studying our motion is not just an isolated task, it is a powerful way to independently verify our entire cosmological model. If the observed velocities significantly deviated from the simulation predictions, it would signal that something is fundamentally wrong with our model. Perhaps the properties of dark matter are not what we assume, or dark energy behaves in a more complex way. But so far, when considering structures like Laniakea and the dipole repeller, the agreement between theory and observation is excellent. This instills confidence that we are on the right track in understanding the mechanics of our universe. The entire narrative surrounding galaxy motion is deeply intertwined with another great cosmic mystery, the nature of dark matter. After all, it accounts for the lion's share of the universe's mass, roughly 85% of all matter, and is, therefore, the primary sculptor of the cosmic web. Ordinary visible matter, galaxies, stars, and gas, merely traces the gravitational field generated by this invisible dark substance. When we discuss the Great Attractor or the Shapley Supercluster, we are referring not just to the combined mass of visible galaxies, but primarily to the immense dark matter halos in which these galaxies are embedded, like raisins in a cosmic cake. Without dark matter, the gravitational pull of these structures would be nowhere near enough to explain the velocities we observe. In fact, it was the study of galaxy motion within clusters back in the 1930s that first prompted the astronomer Fritz Zwicky to propose the idea of missing mass. He noticed that galaxies in the Coma cluster were moving so rapidly they should have long ago flown apart if the cluster were held together only by the gravity of visible stars. Zwicky hypothesized that there must be something else, something invisible, providing the necessary extra gravitational anchor. Today we call that dark matter. Thus, mapping the peculiar velocities of galaxies and reconstructing the universe's gravitational field is essentially a method of mapping the distribution of dark matter itself. We use visible galaxies as test particles whose movement betrays the presence of the invisible substance. This allows us not only to confirm dark matter's existence on vast scales, but also to study its properties. For instance, the fact that structure forms correctly in simulations involving cold, dark matter, meaning it consists of slow-moving particles, provides a powerful argument in favor of this specific model. If dark matter were hot, made up of fast, relativistic particles, it would have smoothed out the small fluctuations present in the early universe. Structure would then have formed top-down, starting with large sheets that later fragmented. Instead, we observe the opposite hierarchical structure. Smaller halos form first and then merge into larger ones. Therefore, every time we speak of our journey toward the Great Attractor, we are truly describing our cosmic plunge into a gigantic, invisible ocean of dark matter, an ocean that ultimately governs the destiny of our entire corner of the universe. It's fascinating to conduct a thought experiment. What if our solar system wasn't tucked away on the quiet outskirts of the Milky Way, but instead sat right in the heart of a massive galaxy cluster, something akin to the Norma cluster at the center of the Great Attractor? How dramatically different would our world and our sky look? First off, the night sky would be utterly unrecognizable. Instead of the relatively calm, familiar band of the Milky Way, we'd be staring up at a celestial expanse studded with hundreds of brilliant galaxies. Many of these would be visible to the naked eye, appearing as large as the moon. It would be a breathtaking and perhaps terrifying spectacle of perpetual cosmic fireworks. Secondly, existence in this environment would be far more hazardous. In the cores of clusters, galaxies are constantly interacting and colliding. The gravitational tidal forces from massive galaxies flying past us could rip stars and planets right out of our own system, flinging them into intergalactic space. The probability of a close stellar encounter, one capable of completely destabilizing the orbits within our solar system, would be drastically higher. Furthermore, the space between galaxies in a cluster is filled with extremely hot, diffuse gas, often reaching millions of degrees. While this radiation couldn't burn us due to its low density, it would create an intense background of X-rays and gamma rays. This high-energy flux would be devastating to life on the surface of planets lacking both a dense atmosphere and a robust magnetic field. Finally, the development of astronomy as a science would have taken a completely different path. On one hand, the sheer abundance of nearby galaxies would have allowed us to understand their nature much sooner and recognize the existence of other island universes. But on the other hand, the crucial discovery of the expanding universe might have been impossible. Within a gravitationally bound cluster, galaxies move chaotically. Their peculiar velocities, the local motion not caused by expansion, would far outweigh the velocity dictated by Hubble's law. Observers in this location would see some galaxies approaching and others receding, and they would be unable to discern the overarching pattern of universal expansion. They might very well conclude that the cosmos is static and strictly confined to the size of their home cluster. So, our current location, on the quiet, peaceful outskirts, far removed from the turbulent centers of galactic megacities, has proven ideal. Not only has it allowed life to safely emerge and flourish, but it also gives us the perfect vantage point to observe the universe and grasp its fundamental laws. We are precisely in the right place to be witnesses to this grand cosmic movement rather than being its immediate victims. To summarize our extended exploration, let us revisit the major milestones and realize how far cosmological understanding has progressed in the last half-century. It all began with the simple and elegant model of the expanding universe proposed by Hubble. Soon, however, flaws began to appear in this model, small deviations known as peculiar velocities, which suggested that local gravity was capable of counteracting the general expansion. Then, by using the cosmic microwave background, CMB, as an absolute frame of reference, we measured our own movement, a flight path of over 2 million kilometers per hour toward the constellations of Hydra and Centaurus. The search for the source of this motion began. The first suspect was the Great Attractor, a colossal concentration of mass hidden behind the dust of the Milky Way. It explained much, but not everything. We looked further out and discovered an even more powerful giant beyond it, the Shapley Supercluster. It seemed the combined pull of these two cosmic behemoths should have solved the mystery, yet even this was not enough. This shortfall led to the birth of the bold but controversial dark flow hypothesis, the coherent motion of a massive section of the universe potentially caused by something outside its observable boundaries. However, more precise observations from the Planck satellite failed to substantiate this hypothesis, sending us back to search for causes within the observable cosmos. The true solution arrived from a completely unexpected direction, the creation of a detailed velocity map of our local environment. This allowed us to define the boundaries of our true home, the Laniakea Supercluster, a giant gravitational basin at the heart of which lies the Great Attractor. The final piece of the puzzle was the discovery of the dipole repeller, an immense void behind us whose push provides us with crucial additional acceleration. Thus, our overall motion is the result of a complex interplay of foreground attraction and background repulsion, essentially falling down a gravitational hill into a gravitational valley. This story illustrates how science moves forward, not in a straight line but in a complex non-linear fashion, proposing and testing hypotheses, making mistakes, correcting them, and gradually moving closer to a fuller and more accurate description of reality. Every step on this path not only solves old mysteries, but also opens up new, even more captivating horizons for future research. Well, our journey following these cosmic currents is now coming to an end. We began with a simple question: where exactly are we going? And yet we've uncovered a portrait of the universe of unimaginable complexity and beauty. We've learned that our motion is far from a simple drift toward a single mysterious destination. Instead, it's a multi-layered process. We are simultaneously being pulled, falling toward the Great Attractor, the massive gravitational heart of our Laniakea Supercluster, while also being actively pushed from behind by a giant cosmic void, the aptly named dipole repeller. And if that weren't enough, our entire Laniakea Supercluster is itself slowly drifting toward the even more massive Shapley Supercluster. What an extraordinary cosmic twist! It turns out we aren't just residing in the universe, we are suspended within a gigantic, living and highly dynamic cosmic web. It is here that the invisible threads of dark matter and gravity orchestrate the fate of hundreds of thousands of galaxies, including our own Milky Way. The mystery that once seemed almost mystical has now found its explanation in the complex, yet profoundly elegant, architecture of our cosmic home. We realize our movement is not an anomaly, but simply the natural consequence of our position within this magnificent, grand structure. Thank you for spending this time with me, diving into one of the most fascinating mysteries of modern astronomy. I hope this lecture helped you not only relax and prepare for sleep, but also feel like you are a part of something truly immense. If you enjoyed this cosmic journey, please give the video a like, subscribe to the channel, and hit that notification bell so you don't miss our next deep dive into the mysteries of the cosmos. And now, here is a question for you to ponder as you drift off to sleep. If you had the ability to send a probe anywhere in the Laniakea Supercluster, Where would you send it, and what would you hope to discover there? Share your thoughts below in the comments. Good night, and may you have clear cosmic dreams.